multiple roots of a polynomial, how can we locate them quickly? And there's this little rule here. If a polynomial does have a multiple root, then its derivative will have that same root. Now the order of it, or the multiplicity of it, will be one less. Let's just go and prove it. So what we're saying is our polynomial has a root of order m at x equals a. Then it'll be times some other polynomial, but that other polynomial doesn't have a root at a. Otherwise it would change the order of the roots. If I differentiate it, well, they're both functions of x, so I have to use my product rule. So write down the first, diff the second, plus write down the second, diff the first, but the first I'd have to use my chain rule. So there's our derivative. Now this can be factorised. It's got a common factor of x minus a to the power of m minus 1. But we're left with this other factor. But how do we know a is not a solution to that one? Well, if we look at that factor, the first term, it's definitely a solution to that, because x minus a, that would give us 0. Look at the second factor, but hang on, we specified it was not a root of qx. So we know that a is not a root of that second factor. So yes, we could rewrite it as x minus a to the power of m minus 1 times some other polynomial where we know a is not a root of that other polynomial. So the order has been reduced by 1. So let's use that idea. We're going to solve this equation, but we've been given an additional piece of information that it does have a double root. Now, why is it useful, this idea? Because it's a lot easier to factorise quadratics than it is cubics. Because I now know this has a double root, I can look at the quadratic, which is the derivative. It would have solutions of minus a third or 3. One of those will be the double root. Which one is the question? It's a matter of testing, and there's a logical choice here. I'm probably not going to look at minus a third, because that would sort of suggest that 3x plus 1 is a factor, and there's no way 3x plus 1 is going to be a factor of the original polynomial. So it looks like 3 is the one to check. And if I substitute that in, so we get 0. It is. I now know x minus 3 squared is a factor. Working out the other one, well, leading term times leading term must give us the leading term, coefficient times the coefficient. The other one's got to be x plus 2. And so I can go and solve the equation. X equals negative 2 or x equals 3. Oh, I like this HSC question. See, because look at it. It came from 1991. What do you notice about the date 1991? Yes. Now have a look at the polynomial. It's also palindromic. I don't know if they did that on purpose because of the year or not, but I thought that was kind of good. You know, both of those were palindromic. Yeah. It's all right. We've got this quartic, but we've been given this extra piece of information that 2 plus b squared cannot equal 4a squared. Okay, we're now going to show that alpha, our root, can't be 0, 1 or negative 1. It can't be any of those. Well, 0 is nice and easy. I can just substitute that in and I get the answer 1, which obviously doesn't equal 0. It can't be the root. But if I substitute in 1, I don't get 0, I get 2a plus b plus 2. Okay. If I substitute negative 1 in, again I don't get 0, I get minus 2a plus b plus 2. But this is where the other piece of information comes in handy. We know 2 plus b squared cannot equal 4a squared. Therefore, 2 plus b cannot equal plus or minus 2a. Another way of saying that is plus or minus 2a plus b plus 2 cannot equal 0, and that's what we got for polynomial 1 and polynomial negative 1. So they can't equal 0. That means our roots can't be either plus or minus 1. Show that the reciprocal is also a root. Well, if I substitute in 1 on alpha, I get this expression. Let's turn it all into one fraction. And have a look now at the numerator. That is polynomial alpha. And we've already said that equals 0. Therefore, this equals 0 as well. Well, that means 1 on alpha is also a root of this quartic. Actually, that pattern will always be true when the coefficients are palindromic. If alpha is a root, 1 on alpha will be a root as well. And that's basically what we just proved. We're now going to deduce this. If alpha is a multiple root, and that multiplicity has to be 2, and then we're going to show that 4b is equal to 8 plus a squared. Remember, we just said that if alpha is a root, then 1 on alpha is a root. So every time we see alpha, we see 1 on alpha. Therefore, if alpha is a double root, 1 on alpha is a double root, because if alpha appears twice, 1 on alpha has to appear twice. That now tells us 4 of the roots, but it's a quartic. It has a maximum of 4 roots. So there's no way the multiplicity could be more than 2. Let's now look at the derivative then, because if it is a double root, then we know the derivative will equal 0 as well. But we know 2 of the roots of this, because remember we've now said alpha is a double root, 1 on alpha is a double root as well. I'll just say the third root is beta. Sum of the roots 1 at a time. I get that expression. Alpha plus 1 on alpha plus beta is minus 3/4 a. Sum of the roots 2 at a time, and sum of the roots 3 at a time. Well, that's nice, because now we know what beta actually is. It's minus 1/4 a. If I substitute that into the first one, I get that alpha plus 1 on alpha is minus 1/2 a. If I substitute it into the second one, a little bit of manipulation now, but I end up with 8 plus a squared is equal 4b. So I'm using both the result that I proved by substituting 3 into 1, that alpha plus 1 on alpha is minus 1/2 a, but then also the fact that we now know that beta was minus 1/4 a. End up with our result. Just a last point there. I think I did mention this to some of you the other day when it was actually a triple root, wasn't it, that it would cut through. But basically, if you're finding tangents and things like that by solving the point of intersection, if you end up with a double root, then that's got to be the tangent, because it'll touch, just like a double root touches the x-axis. Same when we're solving these ones simultaneously. That's basically what that's saying. So if you're finding a tangent to a cubic, you've got a root that has a double root, that's got to be the tangent. Right there.